into this computer. It's recording. Okay, cool. So today we're gonna be talking about what you learned this past week and a half. The big part of it is going to be talking about frequency domain stuff or like impedance and phasors. Uh, and I'll also mention parallel RLC circuits, but those hopefully you know how to do. It's basically the exact same as what you did on the last quiz, just you use the other set of equations. I think I just won't go over those. You had a question about it on your homework. If you're curious about parallel RLC circuits, look at the answer key for the homework. I think that's just not really worth talking about here. You might have a question on that, but I honestly, like, if you do, you just do what you did last week. You just use the other set of equations. Um, so then the gist of what I'm going to be talking about today is mainly going to be talking about phasors, sinusoidal signals, and impedance. So to start with, we have sinusoidal signals. And if anyone has any questions anywhere along the way, either speak up or say something in chat, and I will try my best to answer your question. So sinusoidal signals. So the basic signal we have is we have something that looks a little bit like this. We have some amplitude. I'll call it A. I think he called it Vm in class, but I'll call it A, cosine omega t plus phi. And so what we have here is if we have our voltage over time graph, let's say V of t equals, and we have a cosine that's going to look kind of like that. That would be your cosine. So A is going to be how tall it is or the amplitude. Hopefully this is review from like math class. So A is the amplitude, omega is the angular frequency, so that's going to be how many like radians per second. Everything we're doing in this class is radians. And phi is going to be kind of like the offset. So if we have a positive phi, it's going to be shifted to the left a bit. And if we have a negative phi, it would be shifted to the right a bit. If anyone has any questions about that, please let me know. But hopefully that's just like pretty standard like functions, like algebra stuff or pre-calc or something like that. So the reason we are interested in this, oh, and then one other thing, or two other things. So omega is like if we have our unit circle or something, the angle here can be talked about in radians. So this omega is how many radians per second this cosine wave is going at. So as we all know, the default period of a cosine is 2 pi. So it'll take there's 2 pi radians in a circle, and it takes and if we have kind of just cosine of t, right, then that means our omega equals 1. So it would take so that means we are moving at 1 radian per second, which means that to go around this circle once, it would take 2 pi seconds, because 2 pi times 1 radian per second is 2 pi radians. So what this means, though, is that if we want to talk about our cosine in terms of frequency, which is times per second, the unit for frequency is hertz, which is 1 per second. The frequency is going to be 2 pi times oh wait, no, I have this backwards, sorry. Then you can either write it as the angular frequency is 2 pi times the frequency, because if I say my frequency is 5 hertz, right? That means that in 1 second, I go around a circle 5 times. Then that would mean that I am moving 5 times 2 pi radians around the circle, which would be 10 pi. So if I was moving at 5 hertz, then omega is 2 pi f, which would be omega equals 10 pi. So if you get a question and it's like you have a sinusoidal signal that is 10 kilohertz, or like, so example, 10 kilohertz. Someone have a question? No. 5. So 10 kilohertz, 5-volt amplitude, and I don't know, 30-degree phase shift. I don't think you'll ever have a question like this, but this is just like, what would this signal look like? It would look like V of t equals 5 cosine 10 times 2 pi for this omega, or 10, oops, sorry, not 10, that would be 10,000. So 10 times 10 to the third times 2 pi t plus 30 degrees. Okay, so now that we understand what sinusoidal, oh, and then the other thing, if they talk about the root mean squared voltage, for the purposes of this class, they'll be talking about root mean squared voltage in terms of like they'll say for this cosine function, what is its root mean squared voltage? It is simply that amplitude over the square root of 2. I don't think that'll come up, but if it does, that's what it is. Basically, what that means is if I have a sine wave, the root mean squared is if I square the signal and take its square root. So if I square the signal, right, it would look like that kind of, but it would be taller because we squared it. And then if we take the square root of that, then it would look like this, but properly flipped. So the root, if I take the square and then square root it, then everything will be positive. And then if I take the average of that, so that's the mean of the function that has been squared and then square rooted. Anyway, the long and the short of it, the voltage, the root mean squared amplitude of a sinusoid is just this. I don't think that'll come up, but it was in the notes as something you learned, so I'm just bringing it up here. Okay, so now we get into like the actual part that is probably of concern to you guys. Phasors. So phasors are just a good way to represent sine and cosine waves to allow you to do algebra on them. So if I have cosine, I'll say a cosine omega t plus phi, then I can represent this as a complex number, a e to the j. In electrical engineering, we say j equals -1 instead of I because I is taken up by current already. So it would be ae to the j phi. So if I have, like 10 cosine 3t plus 15 degrees, it would be 10 e to the j 15 degrees. So the key thing here is that we ignore this frequency. We'll get to that later. And we always write them in terms of cosines. So if I were to have a sine, if I had like 3 sine 5t minus 12 degrees, then we'd first have to turn this into a cosine. And the key thing here is that sine of t equals cosine t minus 90 degrees. You can kind of verify this if you have like a sine wave. If I have a sine wave, it kind of looks like that at the origin, and cosine is like up here. So if I want to write a cosine equivalently as a sine, then I'd have to shift it to the so this is our cosine, this is our sine. I'd have to shift it to the right by a quarter of its period. So this goes to here and then it's a sine. But the gist of that is we have this kind of identity. So here we have 3 sine 5t plus 12. This would be equivalent to 3 cosine 5t minus, so it would be minus 12, but then we're subtracting another 90 degrees off of that. So then it would be minus 102 degrees. And then this would become 3e to the minus j102. Yeah. And then the reason this is useful is because if we want, and then the last, probably the most important thing is that we can take this and write it as a complex number by the identity, Euler's identity, which is e to the j theta equals cosine theta plus j sine theta. Basically, if you want to visualize it, if we have our complex plane with the real and imaginary axes, uh, this form of the number you can think of as, so if we have ae to the j theta, it's going to be a number with these kind of properties. So it'll have a magnitude, meaning the length of this line. So if this is our point, so P, or our number, I don't know, I'll say Q, Q equals AE to the J theta. So if this is our point Q, then its distance from the origin is A, and its angle from the x-axis is theta. And just kind of by basic trig, we can say this. So then if we have AE, it would be A times this. So as an example, if we wanted to say, I'm taking this from Zorman's notes from a while ago, if we had some current equals 5 cosine omega t plus 30, I'm just going to use the numbers he has here because it is already written out for me and it'll be good review for you guys. So if we have this, then, and we want to add these two together, kind of the easiest way we can do this is say, okay, we're going to turn these into its phasor representation. And when we do that, we make a capital letter and put a little bar over it just to say that it's not actually the current, it's the phasor representation, or we call it the frequency domain representation. So now it becomes 5e to the j 36.87 degrees plus 10 e to the negative j 57.13 degrees. And if we are to rewrite this in terms of Euler's identity, then it would be 5 times cosine 36.87 degrees plus j sine 36.87 degrees, and then plus 10 cosine negative 57.13 degrees, plus j sine negative 57.13 degrees. Okay, so then from there, we would evaluate what these are in our calculator. So 5 times 0.8 plus j times 0.6, and then plus 10 times 0.6 plus j negative 0.8. And then you can just kind of do the math, add these together. Well, we can just simplify it a bit more first. And then this is complex numbers. You just add the like terms, 10 minus 5j. And then if we want to turn this back into a phasor, so that would be back into this AE to the j theta representation, we think about, okay, we go back to our trig. We say, okay, if I'm at 10 plus 5j, right, I need to find this magnitude and this angle. So the magnitude is going to be just like the distance formula or Pythagorean theorem, however you want to think about it. So A is going to be equal to square root of 10 squared plus negative 5 squared, which in this case is 10 squared plus 5 squared. To square root of that is 11.18. And then the phi, or the theta, or whatever you want to call it, the angle, I'll just call it theta here, is going to be the inverse tangent. Again, this is just like we have our opposite and our adjacent. Tangent equals opposite over adjacent. So therefore, if we, or tangent of theta, so if we want to find theta, we do tangent inverse of opposite over adjacent. In this case, the opposite is the imaginary over the real. So that means, and we're only thinking about like the values. So here would be tangent inverse of, oh wait, this is supposed to be, I have this backwards because it's a negative 5, so this should be on the bottom. But everything else I've said holds. So if we're at 10, negative 5, something like that. So tangent inverse of um, -5/10. And if we put that in our calculator, negative tangent inverse of -5/10 gets us -26.57 degrees. So then if we want to finalize our answer as to what I is in terms of just one sine wave, what we can say is that I equals, so remember, if we can go from cosine to phasor, we can also go backwards. And it's kind of the exact same thing. I'll write those two things I did earlier up here. So A equals square root of real squared plus imaginary squared. And I'll write phi up here. Phi equals tangent inverse of imaginary over real. So here we just simply write A, so 11.18 e to the, oh wait, no. Okay, wait. So first I'll write the phasor form, and then I'll write the time to like the real actual form. So we have our I bar equals 11.18 e j to the, or 11.18 e to the negative j 26.57 degrees, which would then allow us to say that I of t is 11.18 cosine omega t minus 26.57 degrees. And so this, while it's kind of complicated, you can do it very quickly in your calculator. I know in class he like uses these for examples, but you can just like straight up put these numbers into your calculator and it can do all of the complex arithmetic for you. So I'll go over like the one other or the impedances now, but then during when I actually do practice problems, I'll kind of show you how you can just kind of skip half of these steps in your calculator. Um, so now we get to why this is like really useful. So impedance. So if I have a circuit that has some like voltage source that has some sinusoidal function, and then I have a resistor, an inductor, and a capacitor, right? You guys don't want to solve this. You've been doing this and you know how long it takes. So what we do instead is just like how we can turn our voltage sources into phasors. So the phasors is like it's a different representation of it. We call it the frequency domain. If you take like a signals and systems class, it'll make a bit more sense as to what that means, but it doesn't really matter right now. But what we can say is that just like how we can take our voltage or our like real V of t and turn it into our V, we can take our resistor and turn it into some equivalent impedance. And we can take our inductor and turn it into some equivalent inductance. We call them Z's. That's the variable for it. I don't know why, but it is. And so if we have R and we have L and we have C, then the R, the resistor does not change. It affects complex signals the exact same way it affects real signals. For the inductor, the equivalent impedance is J times omega times L. So remember how in the phasor representation of a voltage source, we don't take into account the frequency at all. But for the phasor representation of inductors and capacitors, we do. What this means here is that as our frequency increases, then the kind of resistance of this inductor increases. So the inductor is a bigger resistor for higher frequency signals. The opposite is true for the capacitor, where it is 1 over j omega c, or you can rewrite this as negative j over omega c. So what this means is that for really high frequency signals, the capacitor is basically a short circuit because as this c goes up, then the equivalent impedance would go down. But what this allows you to do is if we have some kind of complicated circuit, we can rewrite it where everything is either a phasor or its equivalent impedance, and then you can treat everything as a resistor. And it makes it really nice and easy. And I will do some example problems. And since everything is a resistor, you can use your node voltage, your mesh current, and your like source transforms, and all the stuff you learned in this course so far. So to start, I will do, what's an easy looking question that I got here? Okay, to start, I'll just do an example of, I might take this from your homework and just show an example of, yeah, this works. Okay, so this is basically, these are just formulas. You can memorize those. And then once you know those, it's kind of straightforward. And what you'll find is that questions will often just give you it already turned from like your capacitance and your inductance into your equivalent impedances. But I'll do one example of finding it. So if we have this circuit from the homework, and this was 50 ohms, and this was 25 ohms, and this is 4 microfarads, and this is, I don't know, it doesn't have a value in the homework, but I'll say it's 3 millihenries for now. And we want to find our equivalent circuit in the frequency domain. We would take our phasor. So I don't know, let's say this was like 10 cosine 4t, making this up. So here, 10 oh wait, no, and the homework it actually had a value. That's important. 10 to the fourth t. So that means omega equals 10 to the fourth. If we wanted to think about this in terms of frequency, the frequency is omega over 2 pi, which would make this like 10 to the fourth over 2 pi is like 1591 hertz, if you wanted to think about this in hertz. But we care more about this. So this would become 10 e to the j0, or just 10. And then the resistors, they don't change. So we still have our 50 ohms here and our 25 ohms here. But then these, we would use those formulas I listed above. If you're curious about where those formulas come from, look at the lecture videos. I don't know. He talked about that in class in depth. So the Z of the capacitor, the impedance of the capacitor, is 1 over J times 10 to the fourth. Remember, we're using this formula or this formula. I'll use the top one actually, or the second one, because that's a bit more useful. So we have negative J 10 to the fourth times 4 microfarads, so 4 times 10 to the negative sixth. So if we put that in a calculator, then you get 10 to the fourth, 1 over 10 to the fourth times 4 times 10 to the negative 6, which is going to be negative J25. So, and you can say ohms, it is technically ohms. And then similarly, ZL would be J omega L, which is J times 10 to the fourth times 3 times 10 to the negative third, 3 microhenries. So that's 10 to the fourth times 3 times 10 to the negative third, which would get us J30. So that's pretty straightforward. You just plug it into the formulas and redraw the circuit. So now, if we wanted to solve this circuit, we could basically just use node voltage or mesh current and like say there's a node here, then we have our currents here, 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 and here. And you can just kind of like directly find stuff. You still do it all exactly the same. It's just when you're using your formulas, sometimes you're plugging in complex numbers now. So with that, now I will get to some actual problems. So let's see. On your quizzes, you might not actually have to solve stuff, which would be pretty cool. It seems like in past years, some of the time they've just asked you to like write equations similar to how you had on some of your node voltage and mesh current quizzes. I'm actually I will go over Oh yeah, this is good. Okay. So we have Vs of t equals 30.77 sine 200t plus 120 degrees volts. And then our circuit looks like this. Okay, this is 108.33 microfarads. This is 0.2 henries. This is 50 ohms. This is 0.2 millifarads. And this is also 0.2 millifarads. And this is Vs of t, which we defined up there. So our step one is going to be transform this circuit into its equivalent impedances in the phasors. So if we want to do that, I will copy it all and paste. And so, as I talked about earlier with the phasors, this Vs of t will simply become its amplitude e to the j120. We ignore the frequent, oh wait, no, not quite, because this is a sine wave. We have to change it a bit first. So sine waves, remember, sine is equal to cosine minus 90. So this would be 30.77 cosine 200t plus 30 degrees. And then this would go to 30.77 e to the j30. So that's what we have there. I'll write this again down here. And make sure you write degrees because j30 is very different from j30 degrees. Just, I don't really feel like it's important to explain why. Just make sure you write degrees. There's probably going to be a point off. Does the equation A equals real over cosine phi still work? Yes, that absolutely works. It's basically the same thing, or it's not basically the same thing, but where was I talking about that? So here, right, you can either, if you find phi, right? I'll write this as phi. If we find phi, then we have a triangle. This looks like this, right? I keep writing theta. This is phi. We have phi, and we have cosine of theta is the real part. Yeah, real and imaginary. And we know that, yeah. So we know that we have the real and we have the imaginary part as the lengths of this. So if we want to find this, right, this is the hypotenuse. If you take the real part, or you take the imaginary part, right, if this is our x and we have theta, we have imaginary, and we have real, then while the Pythagorean theorem does work, yeah, you can also say, I don't know, sine of phi equals opposite over hypotenuse. So that would be imaginary over x. So then phi is equal to sine, yeah, x would be equal to imaginary over sine phi. And likewise, you could do the same thing for cosine. So cosine phi equals real over x. So then x equals real over cosine phi. Personally, I think using the Pythagorean theorem is just like a bit more straightforward, but whatever floats your boat, you can use. They both will get you the exact same answer. Um, so so here, going back to this, we want to find expression. Oh, I didn't say this. Expression for I of t. So if we wanted to do this with what we already know, it would be a large pain and you would not want to do it. So instead, we're going to use phasors. So now we're going to try to find this I, and then we'll turn it back into the time domain. So here, for this 108.3, so I'll say this is Z1, I don't know, Z1 equals negative J over omega C, which is negative J over 200 times 108.33 times 10 to the negative sixth. If we put that into our calculator, 1 over 200 times 108.33 times 10 to the negative sixth is 46.16. So this would be negative J 46.16. Z2, so this is like Z1. This is still going to stay as 50 ohms. That doesn't change because it's a resistor. And then I'll say Z2 is for the inductor. So we have equals J omega L, which is J times 200 times 0.2. I think I can do that in my head. That's just going to be J times 40. I will check that in a calculator to make sure yeah, okay. And then for these two, it would be Z3 comma 4 equals negative J over omega C is negative J over 200 times 0.2 times 10 to the negative 3. I'll put that in a calculator. You could probably do that on paper or in your head, but I will do it in a calculator to make sure I do not mess it up. This would get you negative J25. So what we can write the circuit as is negative J 46.16, J40, negative J25, and negative J25. So now that you have the circuit in this form, you forget that there are any inductors and any capacitors, and you just treat everything as a resistor, and you solve it how you would solve any other circuit. So what we have here, we want to find this current. So if we want to just find the current coming out of the battery, then we just simplify everything else into one equivalent resistor, and then the circuit's pretty easy. So the way we'd start that is we'd say, okay, these three are in series, this 50, the 25, and the 25. So we can rewrite this as, and it's common practice to use boxes instead of like circuit symbols when you're using impedances, because again, you're like abstracting it and you're not really thinking about what the component is. You're just thinking about it in terms of its impedance. So here, this was Z1, this was Z2, and I'll call this Z equivalent 1. So Z equivalent 1 is going to be equal to 50 plus negative J25 plus negative J25. Hopefully that's pretty straightforward. You can see that that is 50 minus J50. And then if we want to simplify this a bit further, we can see, okay, these two, again, I'm thinking of these as resistors. So these two resistors are just in parallel. And the equation for parallel is going to be, this can be Z equivalent 2. This is still Z1. Z equivalent 2 is equal to 1 over Z2 plus 1 over Z equivalent 2. Or you could write this as Z2, Z equivalent, oh, sorry, this is over Z2 plus Z equivalent 1. And so here you can either try to do all that, or I'm assuming most of you have calculators that are capable of dealing with imaginary numbers. What I'd do here is you can just straight plug this into your calculator and it will do it all for you. So if you go to the mode button on your calculator, I have a TI-84, so I will be talking about TI-84s, but I'm assuming like any graphing calculator can deal with imaginary numbers. So if you go to your TI-84, you press mode, it's like on the top row, and then you scroll down to where it says real A plus BI or real to the theta I, and then select that A plus BI mode, then it can do complex numbers. If you want to press I, you do second period, and it will like make an I. In this class, we call it J, but on the calculator, it's I. So if I wanted to do this, right, I would simply say, okay, I'll use that second equation there. We'd say Z2 is I times 40. So I times 40 times 50 minus 50I, and then that's over 40I plus 50 minus 50I. And if you put that into your calculator, it'll do all the work of simplifying it for you. So my calculator got me 400 over 13 plus 600 over 13I, which you can turn into a decimal. So this equals 30.6 0.77 plus 46.15 J. And if you want to do this manually, you still can. I think Zorman's been doing that in class. Me personally, I have not manually done that kind of complex algebra in like ever because the calculator can do it for you. Why would you go through the trouble? You might make an algebra mistake. It's just not worth it. Um, Real quick, I'll turn on my video for like 2 seconds. Let me turn on the light. Uh, I don't know if this will like show up because I'm screen sharing for the people watching the recording, or I can like, there we go. Um, okay, yeah, but if you look at my calculator here, beautiful. Okay, you can see me like, how does this work? How do I make this big? If I stop sharing, does that work? Yeah, sure. That's
Yeah, stop sharing word.
okay. Okay. Let's focus. Come on. Can you guys see that somewhat? Yeah. So basically, the key things here, so you press this mode button, it brings up this big menu, and then you go down to this line here. It says real a plus bi or real to the theta I. This one's actually useful too. You can convert from your like two coordinates to your polar form. But basically, if you just press second here, you can just put it in. And as you can see for this line, I just kind of, I don't know if you can see this at all, but you can very directly just, that's better. You can very directly just write out your whole equation, and then your calculator will simplify it all for you. And then if you want to make a fraction like that, if you don't know how, you press alpha y equals, and then it'll bring up this little menu, and you press that first one, and it'll make a little fraction. And then if you want to change it from fraction to decimal, you do alpha y equals, and then press this bottom one, and it'll do that. But make sure you know, it looks very clear now. Okay, make sure you know how to use your calculator well, because it can save you a lot of trouble. It makes you much faster at dealing with complex numbers. And that's kind of why it's so nice to use phasors and frequency domain stuff. Because once you have it in complex number form, you can just kind of put it into your calculator and it can do it all for you. Yeah, so going back, I'll put my webcam back here. And I'll share my screen again. Okay, start broadcast. Yeah. Okay. Okay. So we're here. And then one other thing, if you want to, I mentioned that there's the A plus BI mode and the real to the theta I mode. If you go to that real plus theta I mode and then just like write out a complex number in like A plus BI form and then just press enter, it'll convert it nicely to the A plus or to the real plus theta, real to the theta I form. I don't know. But I'll just keep going through this problem and explain it as we go. But anyway, you do this math somehow. You either do it how you learned in class or you do it in your calculator and you get there. And then we say, okay, but we're not quite done. We have this. We want to find this simply with one z equivalent 3. Z equivalent 3 is going to be z1 plus z equivalent 2, which is simply z1 is negative j 46.16 plus that 30.77 plus 46.15j. You add these together and you get, let me see what we get here. Oh wait, sorry. I'm doing it in my calculator because I never do things by hand. I have to scroll up to get that number back. Okay. And we get what is basically just, sorry, yeah, minus some rounding error, we can just say that this is just the real part. And once we have that, it's pretty straightforward. So from here, I'm kind of out of space here. I'm just going to circle everything and make it a bit smaller. Uh, Here we go. Okay. So once we're here, now we have our voltage, which was 30.77 e to the j 30 degrees. And now here we have 30.77. That's a familiar number. It's almost like he made this problem well. So if we want to find this current I, then this I by Ohm's law still holds when we're dealing with all of this stuff. So V bar equals I bar times Z would be the new form. So I would be equal to V over Z. So our V is 30.77 e to the j 30 degrees, and then over 30.77. So I equals e to the j 30 degrees. And now if we want to turn that back into our time domain, we say I of t is simply, remember, if we can go from one way, we can go the other way. So our amplitude is just 1. So 1 times cosine of the omega will stay the same from the start to the end. So 200t plus 30 degrees. And that would be our final answer. And what this tells you is that with this input, the current that will be through the circuit is that. Very nice. One other thing, I'll go over if I'll do one example of how you would do the complex math if it wasn't very nice and you weren't using a calculator. So let's say we had that 30.77 e to the j 30 and our z was, I don't know, 30 minus 21j. I'm just making up numbers here as an example. So what we can do is we can convert this into e to the e to the j theta form. As I said earlier, you can do this in a number of ways. Here, I'll use the a equals the square root of the things added together. So 30 squared plus 21 squared to the power of 5. So this would be 36.62 e to the, and then we can do tangent inverse of negative 21 over 30 e to the negative j 35 degrees. And then if I wanted to, so to say this was like I bar and this is Z, and we want to find V, then this would be 30.77 e to the j 30 over 36.62 e to the negative j 35. And what you do here is you kind of separate it into two parts. You have your real part, and then you have your phase section. And if we remember our power rules from algebra 2 or pre-calc, then e to the j 30 over e to the negative j 35 is going to be the same as e to the j times 30 minus negative 35 degrees. And so this would get us 0.84 e to the j 65 degrees. So when you're dealing with it, you just remember how powers work and you kind of just do the arithmetic. But the key thing is you would have to turn this into here first if you wanted to kind of do it by hand. Again, though, you can directly put this into your calculator. You can, your calculator will allow you to do e to the power of I times pi over 6. And that works. It just works. It'll do it for you. So you could say 30.77 times e to the j times pi over 6, and then divide that by, in parentheses, 30 minus 21i, and then press enter, and it'll do all of this for you and spit it out in whatever form you have it tell you to. Yeah. So mess around on your calculator a bit if you want. It can make you do the quizzes really fast. you can skip like half the steps that Zorman does in his work in class, just because TI-84s are very good. And whatever calculators you have that are better than TI-84s are probably better. I just don't know how to use them. So then here, like your I of t would be 0.884 cosine omega t plus 65 degrees. Okay, and then I'll do one more question I think I have time for. But the nice thing about this is there's not really much new stuff. If you understand how to convert this stuff, right? You understand that. This is kind of the important things. If you understand how to do that, then it's really just like normal circuits. It's just instead of real numbers for your resistors, you have complex numbers for your resistors. And hopefully you know how to do complex math. That's not really a topic covered in this class that deeply, but it's something that like you can look up on your own if you still don't understand it that well. Um, so let's say, yeah, I'll do this question. So write all equations to solve circuit. And the circuit looks like the following. Okay, so we have negative J4, 4, 3, 2, 12, 8, J6. This is volts. 5, and J7. So one thing that a couple people I saw messed up on the homework, if you have like, if you're solving for something and you get that your voltage in the frequency domain is like J3, um, it's like J3. You have to remember this is equivalent to a 3 e to the J90 degrees. So this is not like zero. Some people like got this and then converted it back to the time domain and said that this was zero. So J3 would actually be like 3 cosine omega t plus 90 degrees. That's just how it is. So here, and this is actually equal to actually, yeah, that's just what that is. And if you want to be fancy, this is equal to negative 3 sine omega t. You can think about that on your own. So here, this is valid. You can have imaginary values for your power sources. So here, the question is, write all equations necessary to solve the circuit. So if you see something like this, you are just going to say, okay, you have a bunch of resistors, you have some power sources, you just do KVL. And let's say this is our V1 and this is our V2. And this would also be V2 because they're connected right here. These are all like V bar if you want to be particular about it. And then we just do like normal node voltage stuff. So at V1, we'd have V, and this is, let's define this as ground. So at V1, if I think about this downward path, we'd have V1 minus 0 over, and then these are in series, so it's just 4 minus J4. And then plus, if I think about this upwards path, it's V1 minus V2. You can put bars over all of these if you want, over 2. Plus, and then the rightwards path, it would be V1 minus V2 minus 12, because that's the orientation of this thing. So V2 minus 12 over 3, and that would equal 0. So that's your first equation. And then your second equation for your second node. All right. Was he given a problem for which you have to solve for the impedance of a specific component? In class, he did one where you had to solve for C given a specific phase angle. I can talk about that briefly. Yeah, in a second. I don't think from what I can see, I don't think in previous quizzes he's done that. But you did have that question on the homework that was kind of similar, where it was talking about how to make it so that the things were in phase. Basically, if you get a question like that, you just solve it how you would solve a normal circuit, but you just leave the C as a variable until the very end, and then you're going to get some equation in terms of C, and you pick the correct, and then you solve for C such that you get the desired behavior. But I don't really think that would be on a quiz. So if you're worried about that, look at how he did the homework question, I would say. Okay, yeah. So here, V2, um, V2, we have five paths actually going out of this. So we have, I'll start with this leftward one. So we'd have V2 minus, or we could say V2 minus 12 as our parentheses minus V1 over 3, because that would be the current going through this 3 ohm. Plus, I'll say this next path is going down, V2 minus 0 over J7 plus 5 now, because these two are in series, you can just add them together. And then here we have it going down. So now we have V2 minus J6 over 8. And then finally, we have this one going up. Just I always say that the currents are going out unless it's explicitly specified by a current source, because it just makes your life easy. V2 minus V1 over 2 equals 0. And if this was your question and it just said write all the equations to solve, this would be your final answer. You've done it. You can get similar things for mesh current. If he asked you to write the mesh current equations, but don't solve the mesh current equations, then you could do that as well. Um, yeah. Um, hmm. What else could I do? I mean, other than that, like there's not really like it's complicated, but if you understand how to convert to impedances and you understand how to convert to phasors and you kind of get comfortable using your calculator, or you're comfortable with these identities to convert between your A plus BI and your, I'll just write these out. So if I have A plus BI or BJ, I'll write JB because BJ sounds funny. A plus JB, this would be equal to square root of A squared plus B squared e to the J tangent inverse of B over A. And this would be your like equivalent form. Hopefully that makes sense. And similarly, if we have A e to the J theta, this would be equal to A, again, yeah, this is like the identity. A cosine theta plus J A sine theta. So that's, if you don't want to like put all this in your calculator, if you know these two identities, you can do all the complex math on your own. And you can put it out. If you have like, again, if you have like A plus B, JB times C plus JD, this is just like you're doing the multiplication of like x plus 1 and x plus 2. It's just that x squared is now -1. So this would be AC plus JCB plus JBD plus BC times J squared. So this would be AC plus JCB plus BD. Or C, wait, this is CB plus, oh, this should be DA, AD. Sorry. Plus, or then it would be minus BC, because this squared is -1. And then your final answer would be like AC minus AC minus B. Oh wait, no, this is, I really messed this one up. Hold up. Here we go. This is correct. It's D. Again, this is why I don't use it on the calculator because I will mess it up. Yeah. So this would be this plus J CD plus CE plus AD. So like as an example, if I had like 2 plus 3J times -7 minus plus the 3, no, I already used 3, plus 5J, that would be equal to -14 minus 21J uh, plus 10J plus 15J squared, which is -14 minus 11J minus 15, which is -29 minus 11J. However, instead of doing all of that, I could have literally just put 2 plus 3I times -7 plus 5I into my calculator and gotten the exact same thing without having to think. So calculators are very nice. Make sure you know how to use it. And with that, I think we're about out of time. If anyone has any questions, say them now. I'll give you guys like 10 seconds. Okay, I will assume no one has any questions. Yeah. Good luck on your quiz tomorrow. Make sure you know how to use your calculator. If you have any other questions, I don't know, review the homework solutions. Those are pretty good. Yeah. Good luck. And I will stop the recording now.